Hello, engineering students. The purpose of this video is to review alternating current AC versus direct current or DC, and also series circuits versus parallel circuits. So what are these things? How are they different? Why are they important? Okay, so the first thing I want to review is alternating current, or AC. Alternating current comes from generators. So I don't have a good visual for this, but in a generator there's a spinning magnet that every time it goes around it makes the current go one way, then the other way, then back again. So you can see this happening here. This little black box is meant to represent an AC generator. So as a magnet spins inside, it must be spinning slowly, right? Because it's going one way, stop, the other way, stop, the other way, stop. So there's a magnet spinning inside here, and that's generating a current in this wire, but it keeps going one way, then the other way, one way, then the other way. And every time it switches direction, the light bulb goes on, goes off again, goes on, goes off again. And we talked about the fact that this is actually happening. Let me change the frequency here. Sorry. If I change the frequency to the max, now the frequency is 2 Hertz. That's 2 times per second that it's going back and forth. In your actual house, your light bulbs are flickering 60 times per second. You can't actually see it, but this is going on in your house. So this is an example of alternating current. Okay, now let's talk about direct current, or DC. This comes from either batteries or solar panels. Those are the 2 main sources of direct current. So if I replace this alternating current generator, let's say I'll remove it, and then I'll take a battery and stick it in here in my circuit. Now the current only flows one way because the battery has a positive side and a negative side, and the negative charges from the one side want to get all the way back around to the positive side of the battery, and they will keep going until the battery dies, until all of the charges are back together again. Okay, that is alternating current and direct current. The next thing we need to review is series circuits versus parallel circuits. We'll talk about series circuits first. This is when all resistors or all loads in a circuit are in series. What does that mean? That means they're all in a row. The charge must flow through all of them, one after the other. That's what it means for a circuit to be in series. So I'll show you an example of one. Let's see, I've got a series circuit. Oh, that's not right. Sorry. It is right. Okay, so I've got a series circuit here. These are all plugged in. They all have just one battery. Just one battery. This one has one light bulb. So the current, it's flowing here through something called an ammeter that measures the current, because the unit for current is amps. We call it an ammeter. So it's going through this ammeter, which is measuring it, and then it's going through this light bulb. It's lighting up, and back to the battery. Here, when we have 2 light bulbs, the current goes much slower. The light bulbs are dimmer, and you can see that the current was actually cut in half. Why is it cut in half? Because there's twice as much resistance. There's more resistance when the light bulbs are put together in series. And again, when we have 3, the current is divided by 3, right? Originally it was 0.9, now it's 0.3. It's a third of its original value. And those light bulbs get even dimmer because the current is going 3 times as slow. There's 3 times as much resistance slowing down that current. Okay, so this is a series circuit. Just to review, in a series circuit, resistance increases as more load is added. This means that current decreases as more load is added. Okay, now let's compare this to parallel circuits. Parallel circuits are when each resistor or load is in its own branch of the circuit. This means that current chooses which branch to travel down. So not all of the current goes through each resistor. It chooses one or the other. Let's look at an example. Waiting for it to load. This is going to show us, here we go. Okay, now we have a circuit again with only one light bulb. Now I add a light bulb, but now I have 2 branches, so the current can go this way down one branch, or it can go this way down the other branch. What happens now is that in each branch I have the same current that I originally had, but now in each branch that's only half of the total current because the current is splitting, going one way and then the other way. So if I look at what the current is outside of those branches, it's actually double. It's twice as fast as it was when there was only one light bulb. Current increasing, that means that the total resistance must be going down, which sort of should make sense because there's more than one path for the current to go down. That creates less resistance because it's not getting all backed up. See these charges? They get to go this way or this way, so they can speed up overall because they have choices. Again, when we add 3, the current in each branch stays the same as it originally was when there was only one light bulb. But the overall current, when all these branches are joining back up again, is 2.7 amps, 3 times as much as it was in the original circuit. This means that the resistance is a third of what it originally was. There's less resistance in this circuit than there was in this circuit. Let me make a couple of notes about that. So overall resistance decreases in a parallel circuit, which means that the overall current increases in a parallel circuit. Okay, that's my review of the most recent concepts we've learned about electricity. Thank you.